So our last speaker will be Vicente Sierra about detectability and reconstruction of standing accretion shock instability, new results with quant wave burst XP.
Perfect, thank you. Good afternoon, everyone. I'd like to start this last intervention by thanking, of course, our organizers and also the universities, our hosts and friends here at the University of Warsaw, including the university's staff, which all of these people have made possible this amazing and very productive week. My name is Vicente Sierra. I'm a PhD student from the University of Guadalajara, Mexico. And it is with great honor and great pleasure that I'm here to present my colleagues and my work, which we have titled Detectability and Reconstruction of the Standing Accretion Shock Instability, New Results with cWB XP. All right, I'm going to start with a very brief introduction about what have we learned this week about SASI and gravitational waves. From our modeling friends, we have learned this week that SASI oscillations emit gravitational waves on a very specific frequency band below 200 Hertz. We also know, thanks to our neutrino friends, that SASI is a great multi-messenger source because it does not only emit gravitational waves, but also neutrinos. And also from Wednesday Sidolin's presentation, we have learned that SASI meter is a pipeline designed for neutrino and gravitational wave SASI parameter estimation. Sido gave a great presentation about the neutrino part. This time, it is now my turn to tell you about the gravitational wave part of this parameter estimation. Here, I must mention that here we have a gravitational wave model, which is Kuroda 2017 S15. This will be our flagship for this analysis, this SASI meter analysis. We can see, of course, that we have the presence of high frequency features, which are always usually present in the waveform models. And for this particular gravitational wave model, we also have a very strong SASI signal. However, this is not always present on all wave models. So how the SASI meter works for gravitational waves? The first step, well, the first stage actually, is what we call the cWB XP trigger generation. For these, we use cWB reconstructions of gravitational wave events. And on this sense, SASI meter is a plugin that uses event wavelet components, which we refer to simply as pixels. And of course, we're now working with the XP fork of cWB, which, among other interesting things, reduces spectral leakage. We can refer to Sergei Klimenko's presentation for more information on this. We have here an example of a reconstruction, a wavelet reconstruction for the Kuroda S15, specifically at 1 kiloparsec. So this is one of the many examples that we have of these reconstructions, which are the basic text, well, the basic file upon which we will work and perform the SASI meter analysis. The first stage on the SASI meter analysis is actually the G-mode estimation. And the first step for this part of the analysis is to actually isolate the G-mode region, the high frequency features. And for that, what we do is we locate firstly the SASI below 200 Hertz. So what we do is we remove all signals on that frequency band. Once we have this, then we have some pixels in the high frequency feature region. And what we do is we compute the mean cross power root square, which I'll just call CRS. And then we remove all of the pixels that have a value which is less than the mean value of the rest of the CRS values for this region. Then what we do is we perform an initial estimation for the G-mode slope. We do so via a least square linear regression. And for example, we have here, again, this same example for 1 kiloparsec. This is the remaining pixels on the region. And you can see that we have here our initial G-mode slope estimation. Again, this is for 1 kiloparsec, but we can do the same for different distances. For example, this is for 10 kiloparsecs, where, of course, as we would expect, the reconstruction is not that good, but we can still make the same process. And we can see here our estimation on this G-mode slope. Then, of course, we have to wonder, well, of course, sorry, with this first initial of the G-mode slope, we also obtain the time and initial frequency of the G-mode. And then what we do is we ask what values does these estimated parameters have. If the slope is in the physically acceptable range, which is a range that we have established after looking at literature, if it's not in this range, then we discard the event because we can assume that the reconstruction is a poorly done reconstruction, all right? But if the slope is indeed in this physically acceptable range, then what we do is we generate 200 samples out of our initial estimations with a 33% variation. And what we do with these 200 samples is to perform a final G-mode slope estimation. And we do so via minimization of this chi-squared function, where C and M is the intercept and slope. This is the variables that we perform the minimization for. TIC and FIC are the time and frequency of the ith pixel. And of course, you can see that we have here some weight values for our specific purposes. For example, rho I is the CRS of the ith pixel because we have to account for the energy of each of the pixels. We have FIC squared. This is a weight function to compensate for the detector's noise curve because, of course, we know that at different frequencies, we have different contributions for the noise. And lastly, we on this He-I density, well, this is a density function of the pixels around the ith pixel. We introduced this specific parameter because we want to account for the fact that pixels with a certain CRS value will be clustered in, well, clusters with a similar CRS value, of course. And, well, of course, this is what we have done for the G-mode estimation. Here we have an example of the chi-squared hypersurface. Of course, since this is a multivariable function, we could have several different points that are the minimum values. So we obtain a final estimation by obtaining the average of these points. Once we have this G-mode estimation, then we can perform the SASI estimation. And we do so by, again, isolating the SASI region. We do so by selecting pixels below 200 hertz, for a frequency of below 200 hertz. And now we impose a condition on the time duration of this SASI region. And what we do is actually to take the initial estimation for the G-mode time, the G-mode initial time. And what we do is we add 50 milliseconds, and that's what we understand as the beginning of the SASI. This specific 50 milliseconds value is, again, what we find out from the literature. Once we have defined this SASI region, what we do is, again, we discard some of the pixels in this region, and we do so by taking, again, the CRS value and keeping only the values, well, the pixels with a CRS value which is greater than half of the maximum value in this region. We have here, for example, again, this reconstruction for 1 kiloparsecs, and this is the remaining SASI region for this specific case. Once we have isolated the SASI region, then we can perform the SASI, well, the parameter estimation. And for the central frequency, we can see that we take a weighted mean value for the frequency, where again our weight is simply the CRS value of each of the pixels. Next, for the time duration, we use this formula to calculate the time. Here, Tmax and Tmin are just the initial and final time values for this SASI region that we have just established. And these delta Tmax and delta Tmin values are the associated resolution time for each of these values, which actually I have to mention for the beauty of cWB XP in comparison to the 2G version is that these two values are the same. So actually, the SASI time estimation is simply the difference between the initial and final time. I also have to mention that the results that I'll be showing you right now, the SASI time duration is estimated through this formula. However, we are planning on changing this for the next implementation, and that implementation will be to take the time window where 90% of the energy is contained for the SASI region. So let me show you our results. This again is for Kuroda 2017 S15 on O3 data. We have the central frequency estimation and the time duration estimation here for 2G results, and of course also for XP results. We can see, for example, for the central frequency that our values, our mean values obtained for each of the distances is not that different between the 2G and the XP results. But however, what indeed varies is the standard deviation. For example, for 10 kiloparsecs, we can see that the 2G results, which are the old results, the standard deviation is about six times greater than our new results on cWB XP, which tells us that we are more confident about these XP results than we are from the 2G results. Now, for the time duration, we can see indeed a difference between our results. For example, for 10 kiloparsecs, we have a time estimation of 259 milliseconds, while now on XP we have 71 milliseconds. So that's a big difference, right? Well, not that big, but a considerable difference. And again, what differs between these two analyses is the standard deviation. We have way smaller standard deviations on the XP results. This is better observed here for the probability density distributions. This is again for the central frequency. We can see that both distributions are approximately on the same central value, but we can see that we have a narrower distribution for the XP results, which again tell us we are more confident about these results. Where we can see a big difference, again, is on the time duration probability density distribution. For example, on the 2G estimations, we can see that, for example, the largest time duration for one of these estimations is of about 1 second, 1 complete second. While for the XP version, the largest one is of about 0.2 seconds. Also, something that we can observe from our distribution, and that's something that we would expect, is that the closest the source of the gravitational wave signal is, then we have a larger estimation for the time duration of the SASI, because, of course, we are receiving better reconstructions of the waveform. Lastly, here are the G-mode slope results. Of course, maybe I didn't mention it, but the way that we are computing the G-mode slope might be crude, but actually for our interest, which is the SASI, it is good enough for our results. But again, for the 2G and XP results, again, the results may not vary that much between each of the implementations. But again, what indeed varies overall is the standard deviation, where we have now a narrower distribution for the XP results, as can be seen here. On Wednesday presentation by Sidulin, he talked about the efficiency, the detection efficiency for SASI meter. Here we have the 2G results, and we have here now the XP results. On the bottom part of these figures, we can see the receiving operating characteristic curves. And again, we can clearly see that for our new XP implementation, we have an overall overperformance on the detection rate. Especially we can see, for example, for 10 kiloparsecs, we have a better performance now on the XP version. And now on the top of these figures, we can see the histograms for the estimation of the row statistics. This row statistic is just the value of the SNR value. So what Sidhu mentioned on his presentation is that we would expect, for example, here, blue, we have the no SASI waveform. That means that we manually remove the SASI contribution and we perform the SASI meter analysis. And the other one, the kind of pink one, is where SASI, we know SASI is present. Here is the pixel density function and this SNR value. So what we would expect is to have two very distinct distributions in order to being able to speak with confidence and say that we know when SASI is present and when SASI is not present. So we can see that for the 2G results, this is somewhat manageable. But now on our new XP results, we can see that these two distributions are very well differentiated, even in cases, for example, as a 10 kiloparsecs. So these again tell us that we are better at detecting or having more confidence at detecting the SASI part now on cWB XP. To finalize my presentation, I want just to talk a little bit about the future and the next steps for the SASI meter. Of course, we would like to explore the spiral SASI case. And this also leads me to talk about the next bullet, which is, again, this SASI time frequency region was estimated about 3 years ago from literature. So, of course, we are open to suggestions about how could we update, or if it's even necessary to update this time frequency region. And of course, we would like to test our SASI meter with more and more diverse gravitational wave simulations. We have already done with some others besides Kuroda, and we find that, of course, if the SASI is not that strong on the signal, then the reconstructions are not that good. And of course, the SASI meter is not as efficient when it comes to detecting. And of course, I also have to mention that some new gravitational wave simulations have been added to our list after this beautiful week. So thanks to everyone who were so kind to answer my questions during the coffee breaks and for adding more to this list. And of course, lastly, what we would like is just to test joint pipelines. Again, to test, for example, Sidhu's work on the neutrino side, and test it again now with the XP implementation and whichever improvement we can do to SASI meter, and test how good is the joint detection. And that's it. Thank you so much.
So there's equations in the literature that say that the frequency of the gravitational waves from the SASI should increase in time, at least until you get an explosion. So you've used like a maximum frequency of 200 hertz, and maybe that's okay for this Kuroda waveform because it's very, very short duration, so the SASI doesn't have time to grow in frequency. But I think if you use any of a waveform that has a long duration SASI, that you're going to cut off some of your gravitational waves from the SASI because it's going to go above 200 hertz. Ooh, that went funny. So I would advise revising your frequency cutoff.
Yes, that's actually one of the things I've been asking around, including also the SASI starting time, which is something we have to tune better in order to being able to account for those type of cases. Thank you.
Yeah, Jade took my comment, so I can just echo that. But yeah,
thank you.
Jade was for faster.
Yes. Thank you.
Thanks for the very nice talk. So just a quick question, because you showed like how cWB is able to kind of get the time and frequency right of the SASI, which is great. But like, is there any sort of, so let's say we have a real detection and you perform the SASI meter on the real detection. Is there a way of like quantifying how confident it is that SASI actually exists? So of course, reconstruction is one thing, but in real situations, we don't have the injected signal. We can't compare with the true value. So is there some sort of like just like injection parameter or metric that you can quantify your confidence for these detections? Thank you.
Well, no, thank you. I think my answer would be that that it would be awesome to be able to do that, but at this stage, that's all we got, right? So that's why we would like to get a hold into all of the biggest amount of simulations that we're certain that contain a sufficiently strong SASI in order to be reconstructed, so we can test it and perfect it in order to be confident that when we get that that real detection, then SASI meter will be ready to perform the detection and the parameter estimation. So yeah. Yes. Yes. Thank you. Thank you.
Any last questions? Nope. Let's thank Vicente again.